Hey folks, we're going to be doing another first in the Energy Rant this week. We're going to be doing an interview and conversation with an energy expert, this time in energy storage. I'm going to be interviewing Doug Houseman, a visionary in utility and grid modernization. Doug is with Burns and McDonnell. I met Doug through a workshop with Wisconsin Public Utilities Institute on energy storage, and his panel was on lessons learned and what's next in the industry. And I enjoyed Doug's responses, thoughtful, critical input into that conversation, and wanted to dig into that a little bit further as part of the Energy Rant. So I thought it'd be great content. So hope you enjoy. So Doug, you mentioned on the panel that batteries must meet the use case. And to me, that sounds like a supply meeting demand thing. And, the solution needs to fit the problem. Could you explain what that term is, the use case?
So when you talk about a use case for batteries, it might be a power quality use case where you've got sagging voltage for very short periods of time, or under frequency for short periods of time. Or it might be that you have a large amount of excess renewable in one season and not enough power to get through another season. And so you might have to store power for months.
Okay. Excellent.
And so if you take a lithium ion battery, for instance, they self-discharge a little bit every day. So if you're going to shift power from May, June to December up here in the North Country, when you actually do need it, because there isn't much sunlight for solar, you might lose as much as 50% of the energy that you put in that battery. On the other hand, if you were to pump it up behind a dam, with the exception of a little bit of evaporation of the water, which can be contained by covering the reservoir over, you're not going to lose very much in the way of the energy that you put up there.
Yep.
And so that's some of what you want to think about when you pick the storage that you're going to use.
Sure.
It's sort of like, how long does it need to run? Then it's sort of, how much energy do you need versus how much capacity do you need? So if I'm trying to fix a frequency problem, I probably only need to run a second or two, maybe 5. And I need a lot of capacity. I need a lot of kilowatts. But because I'm only running for 4 or 5 seconds, I don't need a lot of energy.
Yep. Makes
and
sense.
Then you want to look at the duration that you want to hold that energy between the time that you get it and the time you let it out. So if you're trying to do frequency smoothing for solar photovoltaic, and that's all you're really looking for, it may be that a flywheel or supercapacitors are far better than a battery.
Okay, got it. That's good to know. The next thing that you mentioned in the discussion that was interesting was I think it was a lithium ion application, and they were expected to have a useful life of 15 years, but the batteries or the system or equipment failed in just 1.5 to 3 years, so only 10 to 20% of their expected useful life. Could you explain how that happened, or could you explain that more,
please? It was a use case mismatch.
Okay.
Lithium ion batteries are best, and I got to be careful here because there are a lot of different kinds of lithium ion batteries.
Yeah,
but the ones that were chosen to go into this application are best if they start at maximum state of charge and discharge to their minimum state of charge, and then fill all the way back up and get cycled once or twice a day.
Got it.
This was a fast frequency response situation where the battery would discharge for 5-10 minutes at most. Then it would charge back up. Then it would discharge. Then it would charge back up. And it might happen 50 to 100 times a day.
Wow.
Well, if you remember the old NiCad batteries that you put in a power tool, and
Okay.
how if you just used them, put a screw or two in every time you used them, pretty soon all you could do was put a screw or two in.
Okay.
Similar things can happen with lithium ion batteries because of the formation of particles called dendrites in the battery every time you discharge and charge the battery. And you pretty much form about the same amount of that debris every time you charge or discharge the battery. So if you do short cycles, you build that up in the battery and reduce the capacity of the battery fairly quickly.
Wow. So it's actually a kind of a physical material issue.
Yeah, so it's a change in the material in the battery, and you build up this debris, for lack of a better term, without going into chemistry and physics.
Okay. I wouldn't understand that anyway, probably at this point.
Neither do I.
All right. So you mentioned there's a lot of different kinds of lithium-ion batteries, and I wrote down that you had mentioned it's not one chemistry lithium-ion, it's 43.
It is.
And could you explain, like, what are the implications for that? And I suppose it gets to what you just talked about a little bit about,
So I'm going to talk about 3 lithium-ion chemistries to kind of illustrate what's going on.
Okay.
There's lithium titanate, which we don't see in cars or hand tools or anything like that, but it's very forgiving for charging very quickly and discharging very quickly. So in Europe, they put lithium titanate batteries between the grid and the bus system. And so the bus stops at the bus stop, and as the passengers get on and off, an arm comes over and goes into the top of the bus, and it gets a very short fast charge.
Wow.
And if you did it directly with the grid, you would cause a voltage sag and other power quality problems. But because you can trickle charge into this lithium titanate battery between the buses, 5 minutes, 10 minutes, whatever it is, and then in a minute, you can discharge all of the energy that's accumulated into the bus without doing any damage to the battery.
Wow, that's fantastic. That's cool.
And that's a very different kind of a battery with a very different safety profile than, say, a lithium iron phosphate. And by the way, you'll see that abbreviated LFP, F for ferrous.
Yep.
That battery is relatively safe in terms of lithium ion batteries. It's what we're looking at right now for most stationary storage. It doesn't have anywhere near the typical car battery density, watts per kilogram.
Yep.
But it will cycle, full cycle, down to its minimum state of charge and then back up to its maximum state of charge relatively nicely for 6,000 to 12,000 times, depending on the specific ratio of iron and phosphate in the battery. And then we get into the battery that goes into automobiles, and that's NMC, nickel, manganese, cobalt. And that's got the highest watts per kilogram of any battery in the world today, which is why it works so well for cars, because you get more energy per kilogram of battery than you do any other thing. It could take as much as twice as much LFP or 3 times as much titanate as it does NMC in terms of kilograms to get the same amount of energy into a vehicle.
Right. Okay.
Now, NMCs are great for vehicles, except that You don't want to start a cell on fire or get it below its minimum state of charge, because NMC batteries can have cascading failures, which turns them into something that for most lay people, they would call it an explosive discharge.
Wow.
Now, it isn't quite explosive, but one battery goes off, the next battery goes off, then 2 more, then 4 more, then 8 more, then 16 more, and so on and so forth. The biggest problem with NMC batteries is they contain their own oxidizer.
Okay.
So they're almost impossible to put out unless you can take the heat away. So the right answer is massive amounts of water to put out or to keep an NMC fire from happening. Okay. In Switzerland, they have actual special tow trucks that effectively have a big tank on the back of them. And anytime an electric automobile gets into an accident, even if it doesn't burn, they put that car in the tank up to the point where it's over where your mirrors are normally at on the car, which means basically car no good no more.
Yeah, and somebody's, I suppose, has got to evaluate whether it's worth. Do we need to dunk the car? Huh?
No, that's a requirement in Switzerland now. If it's an electric car, it gets a trip to the tank if it's been in an accident.
Okay, well, that was meaning like the severity of the accident. Yeah. Oh, that's interesting. Okay. One of the other things you mentioned is that the battery. I don't know if I have the right term or that used or not, but the 20-foot, I call it a battery box, that are common on grid scale storage, require a 30 to 40 kW heat pump load because the batteries are so environmentally sensitive. They've got to be maintained at, within tight temperature bands, and that's a significant parasitic load. And did you and something about diesel generators and having auxiliary power for them?
Yep. So let's
talk about that a little bit.
Let's say I've got a battery that I'm using seasonally.
Okay.
So I use it in the winter, I use it in the summer, but I don't use it in the spring and the fall. Even though I'm not using that lithium ion battery, I still have to maintain its environment very carefully during the time that I'm not using it. Mm-hmm. So that heat pump needs to run during that 2 to 3 month period to maintain the battery within about a 20-degree window. Mm-hmm. And that window specifics is by the manufacturer of the battery. But if you think about it, if you got a 20 or a 40-foot ISO container that's metal walls with little or no insulation, and you got temperatures that are swinging like ours are now, 30 degrees or thereabouts at night, can get up to 70 degrees during the day with bright sunshine, which means the inside of a container might hit 90 degrees during the daytime, all closed up. Even though you're not running that, you may be running the heat pump 12, 16 hours a day during all of that time. And you start adding up, 30 kilowatt hours, 40 kilowatt hours, 16 hours a day for 30 to 90 days that you're not running it. And you've racked up a significant amount of cost.
Yeah. Yep.
And if you've got a long outage, and you still got to maintain this non-operating battery within the temperature range, you may have to stick a gasoline or diesel generator out there with 8 to 12 hours of fuel tank and go do maintenance on that generator on a regular basis in order to maintain those batteries within that temperature range. So lithium-ion batteries have some significant, I'll call it vampire load. that
It's a heck of a
happens.
vampire load, yeah. Yep.
And in the summer and the winter time, if that system was running, on a really cold winter day, if it was charging or discharging, I may not have to heat it because it might be creating enough of its own heat inside. But as soon as I'm not discharging or charging that battery on a really cold day, think about trying to keep a metal box warm in La Crosse, Wisconsin on a sub-zero day.
Not easy.
And you've got to size the system so that you stay above that minimum temperature that's required to maintain the warranty on the batteries during the winter, and also maintain it below the maximum temperature for the warranty in the summer.
Yep. So yeah, it becomes a little bit like combined heat and power. It seems like a great application for a lot of things, but when you add up the things that the costs and other things that like standby power, for example, when you add up the costs to cover those things, it eats into the savings a lot. So sounds similar. Great. Let's see. So you mentioned battery packs need to be repowered about at about 3/4 of the initial cost in years 7 to 10. Does that mean basically replacing the batteries? Because repowering to me, I'm familiar with the term on wind turbines. So it's basically replacing blades and generators and stuff like that.
This is similar. Typically, when you buy lithium-ion batteries, and that's specifically what I'm going to talk about here, because for flow batteries, you don't have the repowering issue.
But they just last.
Just last. You take a vanadium flow battery, and you'll still be using the same electrolyte in 2121 that you're using in 2021. But for lithium-ion batteries, we do 3 things over the life of that battery. The first is we do what's called augmentation. Now, augmentation is adding new batteries into the existing battery system in order to maintain the total energy capacity of the system. So as batteries degrade, and they do, you add a few new ones and put them into the system in order to maintain the overall energy capability of the battery. And some people will augment right away, send them out from the factory, and some of the batteries will actually be turned off initially. And then over time, as the energy quotient drops, the control system, the battery management system will start turning those on.
Okay. Is the quotient, is that like the capacity, is that what that means?
It just means the sum of the energy coming from the batteries.
Okay. Okay.
Then over the next 3 to 7 years, you'll come in at regular schedules and add additional battery racks in order to augment what's there and keep the energy at about the same point.
Okay.
As you get really bad batteries, you'll replace those really bad batteries. And you'll typically do that on the same schedule that you're doing augmentation, so that you don't have to make more trips to the field.
Okay.
But so you're using 2 different programs to maintain the capability of that battery. Come somewhere between the 7th and the 12th year, you're going to get to the point, depending on the chemistry that you're working with and the use case you're using the battery for, where your warranty is no longer valid, and you're going to have to go out and buy replacement batteries, get a new warranty on those replacement batteries, strip everything out that's been put in. And that sort of repowering of the battery. And it depends on use cases. It depends on how many times per day you're running the battery. It depends on how well you stayed within the warranty window and so on and so forth. There are many factors that can affect the life of the battery and chemistry as well as everything else. So you need to understand what that life cycle is. If you're buying batteries for, say, a 40-year building, you may go through 3 to 5 cycles of repowering that battery over the life of that building. And that's not something that many people take into account when they look at a battery. They go, oh, I'm going to build this building. I'm going to put this battery here. It's going to last as long as the building. So that's as its cost. Because a lot of architects, a lot of engineers don't understand the life cycle of a battery.
Sure.
And they find out that there's a significant operations and maintenance cost on that building, which makes it uncompetitive for rent, lease, and so on and so forth. They also find that, at least for some chemistries of lithium ion, there's a significant disposal cost for those lithium ion batteries because they're hazardous waste. We don't know how to economically recycle those batteries right now. The way most people recycle them is to throw all the batteries into a kiln and burn off everything that's not the metals. And recover the metals, and the other 60 to 70% of the battery has to be scrubbed of toxic gases and so on and so forth as it goes up the smokestack.
Yeah.
So you can't just kind of do it in any furnace.
Sure. Yeah. Okay, interesting. So what do you think, going forward, what do you think the long-term best application for batteries will be? We mentioned frequency and, long-term storage. Do you think it'll be some of everything, or do you think it's going to settle into, one of the use cases more than anything else?
Remember, when we talk about batteries, we're talking about flow batteries, we're talking about lithium ion, we're talking about lead acid, which, by the way, is 90% of the batteries that we use today outside of cars. It isn't just a car battery. It's also, most hospitals have great big banks of lead acid batteries. Most data centers have great big banks of lead acid batteries. And one of the reasons they've stuck to it is because they're 100% recyclable.
Cool.
So batteries are going to be just about everywhere. It's just a specific chemistry will end up lining up with 1 or 2 use cases that they're best fit for.
Okay.
And if you walk into a Batteries Plus store, you'll not only see hundreds of sizes of batteries, but you'll actually, if you walk around and look at the chemistries, you'll probably see 50 or 60 chemistries of batteries in a Battery Plus store, which is designed to give you batteries for things you do around the household. We start talking about what we're going to do in industry and commercial buildings and manufacturing processes in transportation. I wouldn't be surprised to see a couple hundred chemistries of batteries, including flow batteries, eventually each settling into the right niche.
Wow. So this is going to be a little, I don't even know what the right term is going to be, but it's almost like we need graduate degrees in, I don't know, electrical or chemical or engineering to figure out all these battery technologies and to apply them appropriately.
Well, we'll eventually get to the point where it's like car batteries.
Okay.
If you got a pickup truck, you're going to get a different battery than you're going to get for a small Chevy Corvette sort of a vehicle. And the manufacturer is going to tell you the sorts of things that work, and you're going to be able to go into a store and there'll be a chart. Oh, you're doing this? Here's the best battery. Oh, you're doing this, here's the best battery. And we'll eventually have, you know, a 12-slide presentation or something similar that will walk you through a little process chart to tell you what battery you want, depending on how you're going to use it. And then a fairly simple calculator for how much of that battery you need.
Okay.
And of course, the NFPA, the National Fire Protection Association, created 855, which is stationary battery storage, which puts a lot of limits and requirements on using batteries in buildings, more limits on buildings where they're occupied, and even more limits on residences. And that's a little over 120 pages of light reading.
Not bad. Okay, I have one last question. You mentioned your earlier your LinkedIn feed, and I think one of the things I saw in there was that we have the United States has 14 seconds of battery storage, grid battery storage right now, and I think your comment was we need 168 hours of storage, or we need to get to 168 hours. And so my question is, how far do you think we'll get on that? What's your guesstimate? How far do you think we'll get toward that?
With batteries?
Just it's storage general, I should say.
Okay.
Storage
with batteries, we'll probably get to 10 minutes someday.
Okay.
If we start looking at all the open pit mines and the old hard rock mines, like the Big John mine up in the Upper Peninsula of Michigan.
Okay.
And what we can do with those from the standpoint of pump storage and mountainsides that we can turn into rail car potential storage and things of that sort. I think we can get there, and I think we can get there without spending anywhere near what people think we need to spend.
Yeah. Yeah. That's,
you know, we're going to have 1 million coal cars in a few years that are capable of taking coal ash and then concrete to cover that coal ash to go on rail tracks laid on the sides of mountains and steep hills. And those coal cars are going to be free. And so that's going to be relatively cheap storage.
Cool. So coal ash must be dense. I did not know that.
Coal ash can be made to be dense.
Okay. So it's kind of like a concrete itself, maybe.
Yep.
Okay. All right. Well, that's all I had. It's been a great conversation. You're a very interesting source of information, Doug. I really appreciate it.
You're more than welcome, Jeff.